So this is our review for summative number 8, and remember this is a no graphing calculator summative. This is your last chance at transformations, so whatever score you get on this test is your score for transformations. We are done retaking it. This is our 3rd time. So do a great job, and if you did fine last time, I'm sure you'll do fine again. So here we have a graph of a parent function, and they want you to apply certain transformations. If there's more than one, make sure you watch the order. For instance, on this first one, a negative in front of the function is going to be a reflection over the x-axis, or a vertical reflection. Oops, that's ugly writing, sorry. And then afterwards it says +3. So as a second step, you're then going to move everything up 3, and it has to happen in that order. So you must first reflect over the x-axis and then shift everything up 3 units. So like for instance, this ordered pair here, which is at 1, 2, 3, 4, what is that, -4, 1. And then this ordered pair is at -1, 1. This ordered pair is at 1, 3. And this ordered pair is at 1, 2, 3, 4, 4, 0. Oh, one more. This ordered pair is at 2, 1, 2, 3, -3. Okay, so when I move over here, the ordered pair at -4, 1 has been reflected over the x-axis, so now it's down here, and then shifted up 3 units. 1, 2, 3. So it's now right there. And then this ordered pair at -1, 1 has been reflected over the x-axis and then shifted up 3 units. Okay, line it up, that's good. This ordered pair, which is at 1, 3 originally, was reflected over the x-axis and then shifted up 3 units. Let's see, this guy here, 2, -3, was reflected over the x-axis and then shifted up 3 units. So that's why order matters so much. And then 4, 0, 1, 2, 3, 4, reflected over the x-axis, doesn't move it anywhere, but it will shift up 3. And this is where I fail life because I can't graph. So, you know what, that is definitely not the worst thing I've graphed in this class, so I'm going to call that a win. Now this transformation kept bamboozling some of you. Anytime it's inside the function with the x, that's a horizontal thing, and you have to remember what it does, and it's always opposites. So a 2 inside the function like this is a horizontal compression of half. Remember, it's opposites. So all of those x values are going to be halved, essentially, is what's going to happen. So this guy, -4, 1, his x value is going to pull back by a factor of half. So instead of being at -4, 1, it's going to be at -2, 1. And then this guy, -1, 1, instead of being at -1, 1, he's going to be at -half 1. This one, which is at 1, 3, instead of being over 1, it's only going to be over 1/2, still up 3. And then 2, -3 is now going to be at 1, -3. And then 4, 0 is now going to be at 2, 0. And then in theory I should be able to connect the points here, but you'd be wrong. Alright. So nothing changed in the y's. It didn't stretch in any direction other than it shrunk actually in the x direction. So keep in mind inside the x is a horizontal movement, and it's opposite of what you would think. So keep those all in mind. That was actually a little more challenging than what you're going to see in your test. So if you could do those fine, then you're good. So here we just want to verbalize what the transformations are. So remember, a negative in with the x is a horizontal movement, so you could call it a horizontal reflection, but it is a reflection over the y-axis. Remember, horizontally it would be flipping over the y-axis. And then +2 off to the side is a vertical transformation of up 2. Now in those cases, these don't affect each other, so any order would have been acceptable. However, in this next question, order does matter. There's a negative in front of your function, which has to happen first, and then in reference to the +8. So you have to apply this transformation first before you do this up 8. So this can either be second or third, but the important thing is that this reflection here has to happen first before the +8. So first, I just like to read left to right if there's nothing to distribute, and this is not a distribution. This is just a negative in front of the function. So reflection over the x-axis this time. It's a vertical reflection. And then these next two steps can be interchanged. So 2 and 3 here, it doesn't matter which order they go in, but I just like to read left to right, so I'm going to go left 7 and up 8. But I reiterate, guys, these two steps can switch. Now here, be careful. There is an outstanding set of parentheses here. So this negative can be distributed to not just the function, the 2f function, but also to the up 5. And that's how I like to approach this question. I like to go ahead and distribute it. And make that a subtract 5. And then I would apply the functions left to right because I've distributed it. However, so if you do it that way, that's great. That means you have first a reflection over the x-axis, and then the 2 in front would be I'm going to abbreviate because I'm a little short on time and space here, a vertical stretch of 2, and then I would have applied a down 5 shift. However, if you are not in the distribution kind of mood, if you would have just gone back to the original one, the negative parenthesis 2 f of x plus 5, an acceptable answer to this one would have been to apply the vertical stretch of 2 first, and then shift it up 5, oops, and then to reflect over the x-axis. So either one of these would be acceptable lists, and actually there's a little bit of rearranging you could do within those lists, but just make sure that you're deciding when you want to apply the reflection and how that affects everything after it in the function. Alright, here, a 4 inside the function is a horizontal, and you got to remember it's backwards, so this is a horizontal compression of 1/4. Remember, it's backwards. And then plus 3 off to the side is an up 3 shift. One's horizontal, one's vertical, so order doesn't technically matter, so you just need to do one and then the other in any order. But you have to know what to call them, and that's kind of the trick to these questions. Last time we tested this, people were getting real confused with the horizontal components of it. This was also an issue for some kids. We have a cube root function this time, so be careful. It's a cube root function that's been shifted 3 to the left and up 4 units, and then they gave me an ordered pair of 5, -12 that we're going to use. So I'm going to start with like a translated function, like a setup of it, and I'm going to leave an a in front for now because I'm not quite sure what that is. We're supposed to find the stretch. We have a, careful, it's a cube root this time, not a square root, cube root of x, and then shift it to the left 3 units would be x plus 3, and then shift it up 4 would be plus 4. So now I'm going to come back through and I'm going to plug in my x and y that they gave me. Still don't know a because I'm trying to calculate that. So let's see, that's 5 plus 3, that's all under the radical, and then there's a plus 4. So in order to solve this, you first would want to subtract the 4 to the other side. And what do we have? A -16 equals a times, this is the cube root of 8, which would be a 2. So dividing both sides by 2. We just found out that a was -8. Good to know. Throw it in front of the function. And now we have the cube root of, the translated part is still here, so x plus 3 and a plus 4. Alright, there's our new function with the a value calculated. Alright, now we have some either words or function notation of what's happening to the original function. So what I want you to keep your eye on is whether things have been stretched. These are the transformations we kept having trouble with. So like this one, I noticed there's no sort of reflection happening, just things have been stretched. Let's figure out how. They're just as high and low as they used to be, but I do notice that all the x values are twice as big as they used to be. So that would be a horizontal stretch of 2. So how do we write that? Well, remember, horizontal is in the function. Oops, it's not f, it's g. Eraser would be better. There we go. So if we took function g and we wanted to stretch it horizontally, that means, remember, think backwards. Now it's actually going to be a 1/2 x. That would be a stretch of 2. Horizontal stretch of 2. Now this one, this time the x values are the same as they were, but I noticed the y values, well, not the zeros because those are boring, but this y value has been stretched by a factor of 2. So this would be a vertical stretch of 2. So, come on, pen. We need to figure out how to write that. So remember, vertical is in front of your function. So you start with function g of x, but to vertically stretch it, you just throw a 2 in front. That's the key difference there. So we have to somehow wrap our brains around the fact that horizontal things are backwards and weird, and what they look like in the function. You have to be really careful. Now, as you practice these, you want to go through everything you do. You want to have your little yellow card next to you. We will have a blue card for you to use on your test tomorrow, but you want to go through those steps. So step 1 says to factor everything. So that's what I'm going to do. This denominator, I bet it factors. So let's go ahead and write everything in factored form. X minus 7 is not going to do anything, but let's see. How about 3x plus 2 and x plus 1. Now, do be careful about factoring, because if you factor wrong, you're going to get a lot of other things wrong. That's 3 plus 2 is 5. Yep. So your domain would be anything that would give you a domain interruption would be a denominator set equal to 0. So if I look at your denominator pieces and you say that they can't be 0, and you can shorthand your domain for me, the x's can't be negative 2/3 when you solve this one, and x can't be negative 1 when you solve that one. Now I don't see any canceling, so when I go to identify any vertical asymptotes, that would be the lines of when you set your denominator equal to 0, so when is your function undefined. So make sure they're in line notation, so x equals negative 2/3 is the first vertical asymptote, that's why there's a discontinuity there, and then x equals negative 1 is the other vertical asymptote. The horizontal asymptote is a inspection of the lead term. So I noticed that this guy is bottom heavy. There's a higher degree in the denominator. So bottom heavy has y equals 0. I need the equation of the line, please. For woo! I didn't mean to do that. For horizontal asymptote. What did I do? Messed up all my pretty notes here. My goodness. All right, plus. There's a plus right there. And then zeros, meaning x-intercepts, would be when you set your, after you look for canceling, then you set your numerators equal to 0. So if you want to change this to x-intercepts, you sure can. But if you take your numerator and set it equal to 0, you get an x-intercept at 7. So 7 comma 0. Write yourself a little note here. And then your y-intercept, these are my favorite ones to find. They're so easy. You just plug in a 0 for all of your x terms. I like to go back to the original problem that was unfactored. It's actually a lot easier to plug in things. So like you think about it being 0 minus 7 over 0 plus 0 plus 2. Well, that ends up with negative 7 over 2, better known as negative 7 over 2, or you can even say negative 3.5. But make sure you're writing this as an ordered pair. So you plugged in a 0 for the x, and you got a negative 7 halves, or you can leave it as negative 3.5. All right. Keeping your yellow card handy. Step 1, factor everything. So this numerator factors pretty nice into 3x plus 1 times 3x minus 1. Oops, except I can't write. Oh my goodness. Okay, try again. And then my denominator also factors, how about x minus 10 times x plus 2. So no canceling happening. But regardless, I do have 2 discontinuities where my denominator cannot equal 0. So my domain interruptions would be x can't be 10 and x can't be negative 2. Because there happen to be 2 vertical asymptotes. So make sure when you're giving me the vertical asymptotes, they are equations. So there's a vertical asymptote at x equals 10 and a vertical asymptote at x equals negative 2. The horizontal asymptote is easiest found back at the original setup, where we look at the lead terms and compare the degrees. So the degrees are equal weight this time, which means your horizontal asymptote is at the line y equals the coefficients, which is 9 over 1, so just 9. And then for x-intercepts, also known as zeros, so remember x-intercepts would be after you factored and looked for canceling that you set your numerator equal to 0. So that's pretty nice and easy. You get positive 1/3 and negative 1/3. please write them as ordered pairs. And then finally, my favorite one, finding the y-intercept, would be where you plug in a 0 for your x. So going up to my function here, 0 minus 1, and then 0 plus 0, or minus 0, whatever, minus 20 is negative 1 over negative 20, better known as positive 1 over 20. Remember, this is non-calculator, so you're not going to want to worry with simplifying too much here, guys. 1 over 20 is a much easier answer than trying to do a decimal in your head. Okay. Now, a little spoiler alert on this one. I'm saying there's a hole, so you're going to have to find it. So our first step, like always, is to factor everything. So I'm going to pull out some crazy factoring. Here we go. Let's try 4 and 1 this time instead of 2 and 2. I think we need to get to a 20. And then, how about a plus 5 here, and then a minus 1 here. That'll add up to 19 in the middle. Alright, in the denominator, we have an x plus 7 and an x plus 5. And then, yeah, I can see that there is going to be a hole right here. This is a removable discontinuity. Remember that fancy phrase? Which we refer to as a hole. So the factor, if you were to solve the factor and get the solution to it, that is the x value of the hole. So there's a hole at x equals negative 5. Your job is now to come back and find the other ordered pair, part of the ordered pair for the hole location. So we would algebraically remove the hole from the problem, and then you end up with a much simpler 4x minus 1 over an x plus 7. So now you go and you take your negative 5 and you plug them into your x's. So what do we have here? We have 4 times negative 5, so negative 20 minus 1 over negative 5 plus 7, which is 2. So that's negative 21 over 2. And again, I'm calculator free at the moment, so I'm just going to leave my answer just like that. But if you wanted to go to a decimal, you sure could. Okay, and then here, write the end behavior equation. This is fancy talk for the horizontal asymptote or the oblique asymptote. So I notice here we have a top-heavy equation, which means we are going to find the oblique asymptote, which requires either long division or synthetic division. Since most of you like synthetic division, and this one would work out nicely in synthetic division, go ahead and do it. 4, and then we got a 1, a negative 5. Uh-oh, be careful, there's a missing term there. There's no linear term. So as much as you love synthetic division, you better be able to perform it accurately. Alright, here we go. Should come out to giving us an end behavior equation. Alright, so 1 times 4 is 4. Add them up and you get negative 1. Now your remainder does not have to come out to 0 on these, so don't panic. This is a negative 4 times 4 is negative 16. And when you add those up, you get a negative 14. So sometimes kids freak out because they're like, oh no, I didn't get 0. Well, this is just the remainder, which is interesting, but it's not actually part of the end behavior equation. The end behavior equation would be the equation that results from these coefficients. Now notice, gigantic capital letters, equation. Don't just write 2x squared minus x minus 4. It is the line y equals, well, don't write 2x squared, Abruzzo, write x squared. X squared minus x minus 4. So before the remainder hits, this is the end behavior equation once you write it in equation format. And then this one's kind of a thinker, but there's a lot of different options here, so don't panic. I want you to write an example of a rational function that has a hole at 5. And a vertical asymptote at negative 7. And then I want you to write another one, just for fun. And leave it in factored form, don't do anything crazy. So for it to have a hole at 5, it means that x minus 5 has to be a removable discontinuity, so you'd have to have something like this going on. And then if it has a vertical asymptote at negative 7, that means that would have been from your denominator, right? So it would have been x plus 7 as a factor. So that's one example. So I'm going to be inspired by that work over here. I'm going to write the same start, x minus 5 over x minus 5. I'm going to say x plus 7. And then, like just for funsies, I'm going to write an extra x-intercept up here. So like x. So it still has the things they asked for. It has a little extra x-intercept that they didn't ask for, but it didn't say anything about I couldn't have extra stuff. You could have put another vertical asymptote down. You could have put like another hole down. There's a lot of things you could have done. So there's not just one right answer to those questions is what I'm trying to get at. Alright, good luck on your test, and remember, this is your last chance at transformation, so please, please, please make it count.